Hello, great. Hello, I'm Derek Sorensen. I'm part of the Ethereum Foundation research team. I'm on the Protocol Snarkification initiative, which is chiefly aimed at safely snarkifying the Ethereum protocol. So SNARKS, zkVMs, this zero-knowledge proof technology, is central to Ethereum's roadmap, to lean Ethereum, to scaling Ethereum, both at the execution and at the consensus layer. What a snark does in practice in this case is that it means that a client does not have to replay all of the transactions, but can instead accept a proof of correct execution, so that a proof that the updated state is the result of correctly applying the transactions in a block to the previous state. Which means that bugs in the cryptography and in the snarks that we're using can introduce, people can steal money, people can compromise the security of the Ethereum protocol, which is, of course, a serious problem. So snarks are critical infrastructure in the long term for Ethereum Foundation, which means that on top of our normal testing and fuzzing and hardening techniques that we need to apply to everything we ship, we need to treat snarks as requiring the highest assurance possible. And therefore, we should apply the methods that deliver high assurance code, in this case, formal verification. Formal verification is a practice where you take a program and you take a formal description of what it means for that program to execute correctly, and then you prove with formal logic that your program satisfies that description of correctness. So this very simple example that I've included on the slide here is, suppose you have a function and you've optimized it. So your function f, you've optimized it to a function f optimized, and the definition of correctness for this optimized function is that it behave the same as your previous function aside from performance. So kind of in an extensional sense, it behaves the same. So we can state this formally by saying that in this case, what's on the screen is a pure functional representation, but you can say for all inputs, for all states, applying f optimized gives the same result as applying f. And that is a formal statement of correctness. That's what you mean. So if we can prove f optimized to be correct with regards to this description, we say that it's proved correct with regards to this formal specification, this description of correctness. And my slide has an asterisk there because there are some caveats that I won't say anything about now, but I will at the end of the presentation. Our work with snarks and zkVMs, as it applies to Ethereum, is to obtain the highest possible level of assurance for zkVMs. Our end goal is a bug-free zkVM. And we're doing this work in 3 main tracks. And I'll give a quick summary of each of these main tracks and then focus on the last one. So the first is we're doing a lot of work at the RISC-V level. All of the zkVMs that are part of the ETH Proofs initiative and that are candidates for the network of provers that will scale Ethereum implement RISC-V semantics at the ISA level. And so they're RISC-V zkVMs. So what we need to do is we need to formally verify that the polynomial constraints implemented by these zkVMs correctly encode the RISC-V ISA. And we have some really good tools to do that. First of all, the RISC-V ISA semantics are available in various Ethereum provers, including Lean, which is the one we use. And also we have developed tooling to extract the polynomial constraints into Lean. So to kind of to take what's in the Rust code and to put it into a place that we can reason about. Side note, by we, I mean about 30 or 40 collaborators in the whole ecosystem. So it's not just the Ethereum Foundation, but it's many, many collaborators throughout. Then at a level higher than that, is the EVM level. Each of these zkVMs will run the EVM in RISC-V. And so these are called guest programs, so we need to formally verify that the guest programs correctly are correct implementations of the EVM, which seems like it might be a simpler task than the RISC-V semantics verification, but it has its subtleties. We have managed to prove, and by we I mean a collaborator runtime verification, has managed to prove that Reth, the RISC-V code that Reth produces, is formally equivalent to a formal model of the EVM called kEVM, which is one of the first and oldest and most storied formal models. So that is a proof of correctness. There are some caveats here and a lot of work to be done. The state transition function was not formally verified in this case, and there are some questions about the boundary of verification. Last and finally is the cryptography track. So we have thus far cared about the implementations of virtual machines and the EVM and RISC-V, taking for granted that the underlying cryptography is sound. But the cryptography that produces a SNARK, a zero-knowledge proof, is actually quite elaborate and complex. And it requires a lot of advanced mathematics and abstract algebra, including finite fields, polynomials over those finite fields that have and elaborate operations on top of those. And so we need some way of evaluating these zkVMs on the basis of their cryptography to ensure that the cryptography itself is sound. I don't know about you, but when I interact with kind of real world protocols, sometimes I'm tempted to take the cryptographic guarantees for granted. But bugs in the cryptography kind of compromise everything at the base level. And this is what I'll be talking more about. To address issues in the cryptography itself, we have developed a library called arclib, this one here in the middle, which is a library of SNARKs and everything that kind of goes into building a SNARK, which I'll get into some more details in a minute. This is part of a large family of libraries. If you go to this QR code, it will take you to the website of our whole project. There's an associated GitHub that has maybe about 15 or 20 repositories that all do their own thing in this ecosystem. And arclib is one of the principal ones of these. It's supported by several repositories. I've included two, the one above and below here. The one above is called vcVIO, and it formalizes all of the Oracle computation. So if you're familiar with SNARKs, there's this interactive Oracle reduction framework where you produce a witness, there's a challenger, and you kind of go back and forth, and that's how you get your probabilistic cryptographic guarantees. So all of that is formalized in vcVIO, and arclib relies on it. And arclib also is fundamentally operations on polynomials, and so we have a library called comppoly, which is a library of computable polynomials in Lean, and it does all the polynomials and field arithmetic. So this is kind of the machinery that we're using. I'll dive a little bit more into detail on arclib as a library, just to kind of give you a sense for what it looks like. So if you go into arclib, it's doing a lot of things. Like I said, it has Oracle reduction, has commitment schemes. Maybe the principal, the core aspect of arclib is this proof system directory. And the proof system includes all the standard proof techniques that you will find in the wild for zkVMs and SNARKs. And so this includes batch fry, Binius, fry, plonk, stir, whir, sum check. Each of these is a large task on its own to formalize correctly, and has experts working on each of these. So here is an example of some of the kind of formal code from the fry spec Fry has various folding rounds, and there's a consistency check on folding rounds. This is a statement that says our specification of Fry in these folding rounds, if you give it a correct witness, the folding round will recognize it as a correct witness, and it will the consistency check will pass. As you can see, the syntax is fairly elaborate. It's one of those things that once you kind of get to know the model and things, it's more straightforward to read. But this is a statement. This isn't actually the formal proof. If you see the by down there in the corner, what follows in the code base is this formal proof of correctness. And so ArcLib is an interesting case study because in the case of formal verification, it's tempting to think that if you formalize a description of correctness, and you prove your code correct with regards to that specification, then your code will just be correct. But specifications can be very elaborate themselves. Cryptography is a good example of that. So in the case of ArcLib, there is kind of a multi-tiered approach. On the base level, we have a formal description of how a proof system should work. And above those, we have checked our description to be correct with theorems like this that check, for example, our description of how rounds should execute in Fry is correct, that it takes a good, correct inputs and it actually, it says correct inputs are consistent. On top of that, for cryptographic protocols, there's what's called a security proof, which takes the whole elaborate scheme of, for example, a snark, and proves that interactive, in this case, this polynomial reduction scheme over interactions with oracles actually produces the cryptographic guarantees. Whoops, there it goes. Actually produces the cryptographic guarantees that we want, and so that is a high level kind of almost like a meta specification. And I guess what I'm describing could easily sound like just this insurmountable amount of work, and one of the limitations of formal verification in real-world production code thus far has been that it is a lot of work to develop these specifications. It's a lot of work to develop the proof tools to formally verify and to write the proofs. But we have seen such, with advances in Gen AI, this actually allows us to speed up our work dramatically, and we can do so securely because it's accompanied by formal proof of correctness. And so what I think a lot of engineering teams are finding right now is that with AI, it can be hard to verify if the code produced by AI is good code, especially when there's so much of it. In the case of these formal languages like Lean that have proofs, the verification process is much lighter because the proof, as long as it type checks, as long as it compiles, is correct, and so you only need to check statements. And so it allows us to dramatically scale our efforts. We also have a lot of expert collaborators on this, and so despite the elaborate nature of this project and the ambitious nature, I guess, we are making rapid progress and expect to be able to formally verify all of these proof systems that will be used in a highly rigorous way. So what is the goal, I guess, of having these ArcLib specs in Lean? The goal is to take zkVMs in the wild, written in Rust, the ones that will run, the ones that, production, they're optimized, all the good stuff like that. And our goal is to formally verify them to be correct with regards to, formally verify the cryptography aspects to be correct with regards to our specification in ArcLib. So that will require some translation between Rust into a formal language like Lean, which is the one we use. So I guess that's one strategy, and we're actively working on that and making rapid progress and expect to be able to do this well. When you translate code in order to formally verify it, from Rust, for example, into Lean, you introduce a trust assumption that the translation is correct. There are a few ways to address this. One of them is to formally verify the translation, which can be done by metaprogramming, which I recognize that what I'm saying, it sounds like we're just formally verifying everything on top of each other. Anyway, that is one way to do it, and it has been done. Not in this case specifically, but it has been done in other cases. It's feasible. Another way to do it is to look at code on the bytecode level. And this previously has been so difficult to kind of tinker with, so hard to read and reason about, that so hard to reason about that it's been infeasible. But again, with advances in Gen AI, this really empowers us to formally reason at a lower level. And so the exact mechanics of how we will formally verify these things are still being decided, but one way or another we will do it. Right, and so circling back to the main goal of this whole initiative, it is to obtain the highest possible level of assurance for zkVMs, and we're aiming at bug-free zkVMs, of course. And now I will revisit this asterisk. So there are always caveats, unfortunately, to formal verification. A lot of mathematicians try to sell it as the silver bullet that will eliminate all bugs, and in a sense, there are some guarantees that you can make, but there are always assumptions that have to be made, which means that we have to employ all of the other techniques that we already, this has to be just an additional technique for high assurance. We need to fuzz, we need to stress test, we need to harden, we need to do everything we can to root out all the bugs that we can. A few of the assumptions that are made that are kind of subtle. The first is the verification boundary. Anytime you prove a program to be correct, you're always proving it correct with regards to a description, and there's always a limitation to that description. You can't describe every last piece of software in the whole world and natural phenomenon. Software doesn't run as an island. So there's always a verification boundary, and you need to keep that in mind. Like I said before, sometimes there are bugs in the specification, but there are ways to address this. And sometimes there are bugs in the proof tools, for example, these extraction tools, which we have methods to address, but also it's worth keeping in mind that formal proofs add a lot to the assurance, a high assurance of software, but we still need to be on our guard. That is all I have for you today. I think we have a couple minutes 3 minutes for questions. Thank you.
Hi, this is amazing, thank you. I'm just wondering, let's say this all goes well and the whole thing gets formalized. I'm just wondering, do any of the cryptography schemes you're using, like Where, for example, do they have assumptions that aren't proven? Like, so that, is there a chance in 5 years you come along and you're like, we made this whole proof, but there was this conjecture in the original cryptography that wasn't there? Or is like everything proven all the way down?
In the case of, I think any cryptography that will be used in production will have security proofs. So these proofs that the scheme actually produces the cryptographic guarantees. Any security proofs have associated assumptions. So there are some. So what the proof actually is that you have these cryptographic guarantees. If you see these guarantees violated, then one of your assumptions is wrong. And so you need to take the leap of faith with these axioms, these assumptions, to even be able to reason about anything. And so, there will be those. Typically, these assumptions are deeply believable, and so seeing a violation will will kind of shatter some concept of reality. But yeah, I get, there are some assumptions that could be there, yeah.
Do you think when like zkVMs start going into like production and you're trying to kind of like test them out on like a kind of a beacon chain type situation where you can kind of get a like pre-production chain, do you think it could be useful to say, similar to like optimistic rollups, you could like create the like zkVM chain, but then also have like a fallback where if there's like, you can basically say like, oh, there's a reward to validators who maybe can naively execute the transactions, and then if they find incorrectness, they get a reward to kind of like, I guess, create like bounties so that so that it doesn't just completely fall apart if there's a bug.
That's a good question. I'm not involved in the discussions at this level. I guess the fallbacks on consensus. I know that before relying entirely on zkVMs, there will be a hard fork where proofs are optional, they're accepted, and then you'll still have people actually executing every block. And then there will come a time where proofs are mandatory. Discussions still need to be had about exactly what that looks like. I think having a fallback is always a good idea. Yeah. Cool. Thank you very much.